So Brian is a water resources extension specialist in the College of Agricultural Sciences, Department of Ecosystem Science and Management at Penn State University. He received a bachelor's degree in environmental health from Indiana University of Pennsylvania and a master's degree in environmental pollution control from Penn State University, focusing on forest hydrology. For the past 32 years, he has conducted research, teaching, extension programs on emerging water resource issues throughout Pennsylvania, including watershed management, forest hydrology, drinking water quality, emerging water contaminants, and climate change. And we love to rope Brian into our climate change webinars because he does a great job in bringing all of these things together. So take it away, Brian.
Okay, thanks very much. Can you see the slides okay there?
It's looking great, and we can hear you great as well.
Very good. Well, yeah, good morning, everybody. Glad to be here today to talk about climate change. I was looking at this presentation a little bit last night and reflecting on the fact that when I first started doing this probably about 15 years ago for this presentation, it was much more hypothetical. And every year it gets more real that we start talking about not what's going to happen, but what is happening already. And we start to get more and more data about what is actually happening. And it remarkably agrees with what we thought was going to happen many, many years ago. So what I want to do first is give some basic information about forest hydrology and just a few slides to talk about how water does move through a typical forest setting before we start talking about how climate change is affecting the various aspects of forest hydrology. And I do have Pennsylvania data in here. Of course, I know you're interested in West Virginia, and from a hydrologic perspective, it's very, very similar. So there's not going to be much in the way of meaningful differences between the data I'll show here and what would be true in West Virginia. The Pennsylvania hydrologic budget, which is just the cycle water movement from precipitation to the land surface and back to precipitation. In Pennsylvania, we average about 41 inches of precipitation a year. Most of that is rainfall, but in some parts of the state, we get significant amounts of snow that add to that precipitation. And about half of that precipitation evapotranspires back to the sky very quickly. So evaporation through the sun and transpiration through plants. So it's about a 50% evapotranspiration, and that leaves about 50% to go into streamflow. And that can happen quickly as runoff, which is shown as 7 inches here, or it can happen more slowly as recharge, which is the 13 inches that soaks into the ground, becomes part of our groundwater aquifers, and then more slowly discharges to streams over time as a base flow component or a groundwater component to our streams, which is why our streams don't dry up in between rainstorms, right? It rains and the stream goes up, but you notice that most streams don't dry up, even if it doesn't rain for weeks. The stream does not dry up, and that's because it's being supported by this base flow component of recharging groundwater slowly over time. So this is a typical hydrologic budget for the entire state, but it's very different depending on the land uses. So if we go to a smaller part of the state, maybe a particular watershed, and look at a completely forested watershed, instead of it being 50% evapotranspiration, it might be 60%, or it might even be 70% evapotranspiration, and a lower component, 30 or 40%, is in streamflow because we have an entire vegetation cover there that's transpiring water. We have more of that water going back up into the sky and less of it running off. Cropland agricultural settings is more of that 50-50 mix, which is what Pennsylvania kind of averages out to, is more of a cropland scenario. And if we go to the other side of the spectrum, into urban settings and pavement, we find that the vast majority of the water becomes streamflow because it has nowhere else to go. There's a little bit of evaporation from the sun that comes off of the pavement, but the water basically just runs off unless it's a pervious pavement. And so we end up getting very high components, maybe 80 or 90% of the water going to streamflow. And that happens very quickly as well, which is another problem. Now, if we look at it even more specifically, the forest component, I mentioned it could be 60 or 70%, and that relates to the composition of the forest. If it is a deciduous forest, it might be 60%. If it's more of a conifer forest, it might be closer to 70%. And there's a lot of differences even within species. So I'm greatly generalizing here, but there can be lots of variability depending on the species composition. Even the age of the forest can have a component in how much evapotranspiration is occurring. Another really unique feature of forested watersheds is the high infiltration rates. And by infiltration, we mean how quickly can the soil accept water or absorb water. And so when we go into a forest setting, if you walk around in the forest, you have that spongy feel beneath your feet of that thick leaf litter, an organic layer, an undisturbed forest, and it feels soft below your feet. And it is basically a big sponge that can absorb tremendous amounts of water, and not just absorb it, but transmit it, because the forest soil is this interlaced network of what we call macropores and even micropores, which are just holes in the soil. And they're formed by earthworms and old tree roots and existing tree roots and small mammals burrowing through the soil. And if you dig a trench in a forest soil, you'll often see this network of small and large holes in the soil, which very much like Swiss cheese are able to just absorb and transmit huge amounts of water through that soil. And as a result, we end up with very high infiltration rates in a forest setting that in some cases can be more than 15 inches per hour of water. So what that means is if it's raining outside, if you hear much about rainfall rates, a heavy rain is maybe an inch per hour. A really heavy rain is getting up into 2 and 3 inches per hour. Hurricanes may be slightly more than that, but you never hear about 15 inches per hour. That just doesn't happen as far as precipitation. And that's what it would take to generate overland flow in a forest, because the soil can take on 15 inches per hour. So you have to exceed that to actually produce runoff. Otherwise, it all absorbs into the soil. Now, the forest can't keep that up. That's at a dry condition, and that's initially, and it's going to go down as it wets up a little bit, but it's still a tremendous amount of water that can be accepted by the soil in the forest. And if we compare that to a lawn, it might be half an inch or an inch per hour, depending on the type of soil and how compacted it is. And then again, out on the end, we have pavement where it's basically zero. I have old logging road on here just to show that when we damage a soil, if we go in and run over it with a skidder and compact it and damage and reduce all that macropore structure down, it will recover if we leave it alone. An old logging road here is all the way back up over 5 inches per hour, even though at one point it was basically like pavement. It was compacted so hard. So over time, nature will restore that infiltration rate. Even on lawns, we can restore it by doing things like aerating and reducing the amount of compaction. But this infiltration rate is really critical because it allows for a buffer to climate change in some ways. It provides this huge reservoir for water to be stored in the watershed and transmitted slowly. And this gets into the residence time, which is how long does it take once water is intercepted on the forest floor, how long does it take before it shows up in a stream or a river or a lake? And you can see these different flow paths on here going from days and weeks and months to even years. And we can actually age water. We can go to a stream and collect a water sample, and we can tell you with some degree of certainty how long ago that water fell as precipitation. And that's going to be an average. Some of the water in the bottle fell very, very recently, and some of it much longer. But if we average the age of that bottle of water, we can do so with natural isotopes of water. And here's some data. This is from West Virginia, the Furno area, the watersheds 3 and 4 that we did back a long time ago now in the late 1980s, early 90s. And this is using an isotope of water called oxygen 18, which is a naturally occurring isotope. And you see the sine wave of the precipitation throughout the year, which is very characteristic of the oxygen 18 in precipitation. And you notice that the groundwater base flow in these streams has a similar sine wave, but it's attenuated and it's offset in time. And that offset we can put into models to calculate how long on average is it taking that water to move to the stream. And if we do that for a lot of forested catchments, we find that it's many months to even several years of residence time, which means that's the average flow paths that we're seeing in forested catchments. When water intercepts the forest soil, it can take months to years for that water to eventually come out as base flow. Now, again, some of that water moves a lot quicker, but the average water is going to take that long to move out into the stream and become surface water. So that's an important component that provides us some buffer to this climate change. It provides us storage. It provides us a time buffer as well within the watershed. Now, if we look graphically at a typical forested catchment, this is a central Pennsylvania watershed. At the top left is what it looks like at base flow conditions. And base flow means it hasn't rained for a few weeks. So the stream is low. You notice the stream is trickling in this case. This is in the dormant season. It's in November. You notice no leaves on the trees, and the water in that stream is comprised 100% of groundwater. That is all water that is absorbed into the watershed from past rainstorms and is now slowly being trickled back out into the stream. So it's 100% groundwater. It takes on groundwater temperature, which is usually around 50 degrees Fahrenheit, and it takes on groundwater chemistry. So the kind of rock that the watershed has will determine what the chemistry of that water is going to be like. Now, the same watershed from the same perspective in the bottom right is now much different. This is during a storm, rain on top of snow. This is in March. And we see now that the stream is flowing very high, but a couple of things we notice is the water is quite clear, unlike in an agricultural or urban watershed where it would be very turbid. It's very clear because the soil has been held onto by the forest root, or excuse me, the tree roots and the vegetation roots. But the interesting thing is that the water getting into that stream is not flowing over the surface even when it rains. It's all flowing underground. It's all subsurface flow. And that's a very unique feature of a forested watershed, is that even during the most intense rainstorms and rain on snow, the water going to the stream is still moving underground to get there. It is not running over the surface because it cannot exceed that infiltration rate that we talked about earlier. And that's a really important component of forests that we try to mimic when we urbanize areas now. If we develop areas, we talk about green infrastructure. And green infrastructure is really all about just mimicking what the forest is already doing, which is to absorb water into the ground naturally and slowly release it into the stream. So generalizing the forest hydrology, we have these really high rates of evapotranspiration. We have a lot of recharge of water getting into the ground to recharge our groundwater aquifer, a lot of subsurface flow and virtually no overland flow or runoff. What that does is produce streams that have moderated flows. They never get really high and they never dry up. The water stays nice and cool because the water is all coming from the subsurface. The banks are stable and we have generally very high water quality. Now, let's mess this all up with climate change, and we'll also talk a little bit about land use at the end. Now, this is some data from the Mid-Atlantic Forest Ecosystem Vulnerability Study that shows temperature increases and precipitation increases. I want to focus mostly on the precip increase, about 0.04 of an inch per year. So over a 100-year period, we're looking at 4 inches of water more than we used to get. Doesn't sound like a tremendous amount, but when you're talking about 40 inches being the annual average, and now you're getting 4 inches more than that, that's pretty significant, right? That's a lot more water. And it's not just that it's getting wetter, it's how that it's getting wetter is so much more important. And I would argue it makes forests even more and more important as we go forward because of how this precipitation trend is changing. Forests are really the only way we have to adapt to that changing precip protocol or scenarios. Now, first, the evapotranspiration trends. What are we seeing and what do we expect to see? Overall, we expect to and have seen increases in evapotranspiration in any vegetated system. When you increase air temperature, which we know we are increasing air temperature, you're going to lengthen growing season as well. And when you do that, you provide more opportunity for the trees and the plants to evapotranspire water. So we know that ET is increasing because air temperature is increasing, and also because there's more moisture, and we'll talk about that in a moment. There's more moisture available to the plants. And keep in mind that a lot of these plants have the capacity to take on more moisture. A lot of them are demanding more moisture in the summertime. You can't even reach their peak amount of evapotranspiration in a typical summer, so they can take on a lot more water and evapotranspire it away. Now, evapotranspiration in the winter is going to decrease, or has decreased, with decreasing snowpack. And we'll talk more about snowpack here in a moment as well. The more interesting component to this, and the one that's probably most obvious to people, and as I go around and talk to the public, the one thing about climate change that people always notice is precipitation. I've had so many people come up to me at meetings and say, you know, I've been farming for 50 years, and boy, it rains harder than it ever used to. It doesn't rain maybe more than it used to. It just rains a lot harder, more intense rainstorms than we used to have. And it produces a lot more flooding than it used to. And the data bears that out, and I'll show you that in a moment. But some of the things that we are seeing is increases in winter precipitation, but it's not translating into more snow. It's just more rainfall in the wintertime and less snowfall and more overall precipitation. In the summertime, we're not seeing tremendously higher amounts of precip, but we are seeing increasing intensity of precipitation, which creates its own share of problems. And we, again, are already seeing this more extreme precipitation. This is data, again, from Pennsylvania, from the state climatologist. And this is showing large rainstorm days. So we would define this as a day where we get more than 2 inches of precipitation. And that's a lot of rain to get in one day. 2 inches doesn't happen all that often. You can see in a lot of years, it's maybe 5 to 20 days per year, something like that. But you see an increasing trend. And if we look at Pennsylvania climate stations, we see this at every single climate station where these large rainstorm days are increasing in numbers. And this just goes to 2011. And if we were to extend this out to more recent data, that trend has continued, where we continue to see these larger rainstorms occurring more frequently. And if you look at the National Climate Assessment, that is most pronounced in the Northeast and Mid-Atlantic region, including West Virginia, where there's been a 71% increase, observed change in very heavy precipitation. So this is not hypothetical. This is actual data saying that there's 71% increase in this very heavy precipitation. Most of the country has observed at least some increase in it, except for Hawaii, but it's generally been less than it has been in the Northeast and Mid-Atlantic region. Now, the importance of increasing precipitation is there's obviously a link between precipitation and stream flow, right? The water's got to go somewhere. Evapotranspiration can't compensate for all the extra water. You're still going to increase stream flow in some way. And there's a very direct relationship between stream flow and precipitation. This is data for one forested watershed here in Pennsylvania, Bushkill Creek, which shows the precipitation on the horizontal and the stream flow on the vertical. And you see a very good relationship. The more precipitation you have in a year, the more stream flow you're going to produce. So we know that if we increase annual precipitation, we can expect to see an increase in annual stream flow. The only question is how much of it's going to be compensated within the watershed. So in a forested setting, how much of that actual annual precipitation can this forest evapotranspire instead of allowing it to flow into the stream? In an urban watershed, it's a much more serious condition because there's really no system to attenuate this extra precip. There's nothing there to remove the precip. At least in a forest, we have something to try to offset at least a little bit of this extra water. So the stream flow changes that we expect and that we're already seeing, higher winter runoff, again, because of rain instead of snow. We had not this past winter, but the winter before was our least snowy winter ever here in central Pennsylvania since records have been kept. And it was a continuation of one of the least snowy winters. We've had very few even average winters over the last 10 years. So snow is becoming less and less common. Rain throughout the wintertime is becoming more common. And that has a lot of implications hydrologically, which we'll talk about here in a moment. Increases in groundwater from greater recharge because we don't have as much frozen soil in the wintertime. So it used to be that from the hydrologic cycle perspective, we expected groundwater to become very stagnant in the winter because we would start getting snow and frozen soil. So there was no movement of water into the groundwater. So the groundwater would just sort of become stable throughout the wintertime. It wouldn't be going up, it wouldn't be going down. Now, instead, in the wintertime, we see groundwater recharge occurring because the soils are not frozen and we're getting rain, and that water is able to actually recharge. So we're getting more recharge of groundwater in the winter and less in the spring when we used to get it. The more traditional approach was the snow all melted in the spring and the soils melted, and that's when the big recharge occurred of our groundwater aquifers. Now it's more broadly throughout the winter and spring rather than a peak recharge period in the springtime. Also, more extreme flows from higher intensity storms. As I said earlier, we're seeing those more common days with 2 inches of precip. That has ramifications for streams, right? If you put that much water down, you're going to see more high flows, which has problems for storm flow, flooding, etc. Now, some of this is offset by the increased evapotranspiration and longer growing seasons with more moisture and a decrease of large rain on snow events in the spring, because has been much of our traditional flooding problems in the mid-Atlantic region, have been these rain on snow events in the springtime, which are a double whammy, right? You have all the rain, which also melts a whole bunch of snow, and you end up getting double the amount of water that you would have if it was just precipitation. If we take away that snowpack, we reduce the risk of those flooding events from rain on snow, which will, again, somewhat offset what we're seeing with this increased precipitation. So, I mean, there's a lot of complexities here. Overall, more water, but we may in some cases see less flooding in areas that were prone to those rain on snow events. These were some predictions of streamflow changes, which have largely been borne out. This data is a little bit old now, but the blue areas are where they were predicting increased streamflow. The oranges and reds were where they were predicting decreased streamflows. And we're seeing this again in actual time. We're seeing more streamflow in the mid-Atlantic region than the Northeast, and lower streamflow, in fact, record streamflows now in the West and the Southwest. I mentioned snowfall earlier, and I know these graphics are very small and hard to see, but what they're generally showing is that the oranges and reds show lower snowpacks compared to average, and lower duration snowpacks, meaning they don't last as long as they used to. So again, if we reduce these snowpacks down, and some of these changes are quite remarkable in the number of days of less snowpack, and the amount of snowpack reduction is pretty remarkable. And again, that will reduce that rain on snow event problems, and will create more rapid groundwater recharge in the winter and spring when we traditionally got it more in the springtime. Now, the temperature increases, which I haven't talked much about, air temperature increases is what I'm referring to, also has implications for water temperature. We know the two are very strongly related. This is just some example data for the Delaware River, which shows the air temperature on the horizontal and the water temperature on the vertical. And of course, they're related, you know, that they're interacting with each other. So if you have a warm day and air temperature, you expect the water temperature to also increase. And so if we are increasing air temperature as we are, water temperatures are going to do the same thing. And that has a lot of implications for what lives in those streams. And there's, the good thing is, from a forest perspective, there are some buffers to that. So this is a complicated graphic, but it shows, first of all, the thermal sensitivity on the vertical axis, which means higher up on the scale means that the watershed is more sensitive to temperature changes. Stream order is the size of the stream. So a first order stream is a tiny little stream up in the headwater forested areas. An eighth order stream, which would be a larger river. So we're moving from small streams to large streams from left to right, and we're having more thermal sensitivity from bottom to top. The BFI, the color coding on here, is the base flow index, which just tells you how much that watershed is influenced by base flow. So what we see on the left side of that graphic is that these streams that are marked as groundwater fed, these are mostly our small streams and headwater areas. They're dominated by groundwater, so they have very high base flow indices. Very blue colors to those dots tells you that they're dominated by base flow, which means they're going to be less sensitive thermally. Whereas the larger streams are going to be more sensitive thermally because they're less dominated by groundwater. So in the forested setting, we have at least some buffer here because of the dominance of groundwater, which goes back to that high infiltration rate and high recharge of groundwater. That system really helps us to buffer somewhat the thermal sensitivity of those streams, meaning they're going to be less prone to temperature increases with air temperature increases, but there's still going to be some sensitivity to it. And where we really get concerned about are species that are kind of on the verge, something like brook trout, which you know, they have a very tight tolerance of temperature in the stream. And when you have streams that are very close to already having high temperatures, it only takes a very small increase to put that stream over the edge. And it only takes a very short time period to kill brook trout if you get the water temperature high enough. And this graphic shows some of the stressors on brook trout in Pennsylvania. And there's lots of different stresses from impaired from population and habitat, and also climate in red. And you don't see a lot of watersheds on here that are color-coded red yet, but that is expected to change over time as air temperature continues to increase. some of these streams that are right on the cusp of having high water temperatures will go over the edge of that and produce toxic levels that brook trout won't be able to tolerate. I know I do some trout fishing, and I noticed this year on one stream, the first time ever, I saw signs on the stream warning anglers about not fishing due to high water temperatures. And this is on a relatively groundwater dominated stream. I've fished there for a long time. I've never seen those signs before. And it points out the problem that we have with increasing air temperatures and trout. There are cold water species, and there are going to be more and more streams that are going to have problems with high temperatures, at least during short time periods. And that's all it takes to really reduce a population, is a short, intense heat time to increase that air temperature and get the water temperature above the threshold level. So what kind of changes are we seeing to the hydrographs? And the hydrograph is just the flow of water over time. So this is showing stream flow over time throughout the year. This is an actual hydrograph for a forested catchment. And this is a more typical hydrograph from years ago, where what we would find is in January and February, the streams are fairly low because it's all snow and ice. And then March and April, you get all of these peaks because of snow melting and rain on top of snow. Summer, you get mostly low flows with an extreme event here or there, which are often caused by tropical systems. And then in the fall, you have generally lower flows as well. What we are seeing is that these peaks in the springtime are shifting to the left, and they're occurring now in December and January and February, and they're lower because there's less snow occurring. So we're kind of spreading out those peaks and moving them into the winter time. We're still seeing these extreme flows, and in fact, making them even more extreme. In the development that I lived in 2016, we had a 1,000-year return storm, which means that we had a rainstorm that occurs once every 1,000 years. And a couple years later, we had a 100-year return storm. Those should only happen not even once in your lifetime, and they've happened just within a few years here in central Pennsylvania. So we are definitely seeing these extreme events much more frequently, and they produce extreme flows very often in the summer or early fall. We're also seeing the higher water temperatures. That's been documented in many places and many times, both in large streams and, as we mentioned, even smaller streams, although somewhat attenuated. And then finally, you can't talk about this without putting urbanization on top of it, because that's another stressor in addition to climate change. We have urbanization occurring all over the country. And this was a study we did with the Environmental Protection Agency. And now it's been almost 20 years ago that we did this study, but we looked at both urban and forested watersheds. We had 39 urbanizing watersheds and 21 watersheds that had stable land use, and they were almost entirely forested or rural. And we looked at the time period from 1930 to 1990. And the concept here was that the past period of record can give us some hint of what will happen in the future, because we already know, based on the past record, how a watershed reacted to a temperature increase or a precipitation increase. And can we then use that to predict forward what will happen in that watershed as we continue trends of changing temperature and precipitation? And not only that, but how does urbanization interplay with this? Do urbanizing watersheds get affected more with climate change, or do they actually get affected less with climate change? And so here's an example forested watershed, Bushkill Creek in Pennsylvania. And what we found was that over time, first of all, you notice the urban land use didn't change at all from 1930 to 1990, and the stream flow hardly changed at all. Now, this is a trend line. This is not the actual data. So if I showed the actual dots, there would be a lot of dots scattered around that line. But I'm just showing the trend line here, which if you look at it real close, you can just barely see that stream flow is increasing because of increasing precipitation, but it's a very, very slight increase, and it's very muted. So on these rural and forested watersheds, we do see increasing precipitation, and we do see increasing stream flow, but it's very muted compared to the urbanizing watersheds, presumably due to the fact that we're getting some compensation from higher evapotranspiration. Now, on an urban watershed, here's Chester Creek. You can see the urban land use skyrockets from almost nothing in 1930 to a heavily dominated urban watershed by 1990. So over a 60-year period, the watershed really almost completely urbanized. And you notice the streamflow trend here is much different. We go from annual streamflow of about 13 inches to about double that by 1990. So we definitely see a greater response. Now, a lot of that response is the changing land use, right? We have to tease out the land use and the climate change between these, but we definitely see a higher response even when we remove the land use change. We see more increases in precipitation in the urban watershed per unit of precipitation. And we see a lower response to increasing temperature in the urban watershed, which again makes sense. In the forested watershed, you increase temperature, you're going to increase evapotranspiration because you have all of the vegetation there. In an urban watershed, you increase temperature, you don't have that same feedback of increasing evapotranspiration as much. You're going to increase evaporation a little bit, but you don't have all that vegetation to increase the transpiration. So we see a lower response in the urban watersheds related to that, somewhat of a difference between the urban and forested watersheds. So in summary, we see changes in forest hydrology, and we're already seeing changes in forest hydrology that include increased precipitation. And I don't think anybody can argue that. It's one of the most obvious things that we see out there today. More extreme events and less snow. You don't need a lot of data to see that. All you have to do is live in this area and you know it. Increased evapotranspiration is going to occur because there's more moisture, more precipitation occurring. There's higher temperatures and there's longer growing season. And overall, we're going to see more stream flow and more extreme flows resulting from greater groundwater and higher precipitation, and especially more intense precipitation. So we're going to see more flashiness where we get more extreme events. And we're also going to see just generally more stream flow. Now, the reason I think that forested watersheds are going to become more and more important with climate change increasing over time is that they do provide a system to compensate for this extra water, right? They do have the extra evapotranspiration. If we continue to urbanize and develop without proper storm flow that mimics forested areas, we're going to have a double-edged sword there, where we have more precipitation and more intense events occurring in areas where we are changing the land so that it cannot accept that extra water. And engineers always say, well, we can just engineer systems to handle that. No, you can't. You can't engineer a system to handle a 1,000-year flood. I can show you in our development what happened with a 1,000-year storm. The stormwater systems that were engineered failed miserably, and you would expect them to, because to engineer a system to handle that size of storm, you would need huge engineered systems that would be incredibly expensive, and nobody would pay for that. So you need forested or forest-like systems that are going to be able to compensate and actually be able to transmit all this extra water. Other things that we're seeing, of course, increased stream temperatures, which have the implications we mentioned, and water impacts on urbanizing watersheds are going to be more extreme, and they're going to be dominated by land use changes. And we see a lot of that in certain parts of Pennsylvania where land use is the biggest effect on hydrology, even much more so than climate change right now. So with that, I will be glad to answer any questions that you might have.
Thank you so much, Brian. Yes, if there are any questions for Brian, please unmute and go ahead and ask those. If you feel more comfortable, you can also drop those into the chat box and we can address those one by one. If we just wait long enough, someone's going to have a question. So great presentation and a very open-ended question. What are the implications for forest management?
Well, I don't, there's only so much you can do to change how this is going to end up, right? you can't change forest hydrology very easily. You can do things when you're managing the forest to try to promote infiltration, for example, and minimize disturbance areas as much as possible. And even when you're doing forest management, trying to minimize soil compaction and simple things like that that are part of BMPs anyway, to try to maintain the natural flow of water within a forested ecosystem. But other than that, I struggle to think of ways that you're going to change any of this or have much of an effect on any of it, other than preserving the forest is what I preach to people as much as possible. And if not preserve it, mimic it as much as you can through green infrastructure to try to make sure that we're creating systems that are going to be able to handle as much of this extra water and extra air temperature or increased air temperature as we possibly can. Like I said, you can't possibly engineer for some of these changes that are occurring. You have to think of ways to prevent the runoff from occurring rather than trying to just deal with the extra runoff.
And we have a question: if there were a larger duff layer, would that help forest floor storage, water storage?
Yeah, it does increase somewhat the forest floor storage. Now, the soil is still the major storage area, and it can store tremendous amounts of water compared to what's on top of the forest floor. But yeah, that does provide some increased storage.
Other questions? We have one from Rick. How important is restoration of forest roads?
Well, very important, because a lot of times you find that forest roads are located right next to streams, right? So they become a very easy way for runoff to occur. And when you get these really heavy rainstorms in particular, you can get a lot of runoff coming from those roads, which creates a lot of erosion, and not only that extra water, but a lot of sediment as well. So restoration of roads, retirement of roads that aren't being used becomes really critical to increase that infiltration rate and recharge rate that we talked about with that retired logging road, but also just creating proper water transmission areas along those roads, grading them properly, and having the culverts in the right alignments and the right locations to handle all that extra water, and try to keep it out of the stream, try to create storage areas for the water along those roads as much as you can, where the water can infiltrate into the ground, or at least be released slowly, like a retention basin would do, into the stream slowly. It's all very critical just because of how the roads are located compared to the streams.
Great. And Greg Nowacki, who gave us a great presentation on restoring fire to oak and hickory dominated systems earlier this morning, has a question. Any thoughts on declining water yield associated with emesification?
Any thoughts on declining water yield? Not something that I have any expertise on, so I really don't have any thoughts on how that might affect things.
Okay. Looks like Greg also posted an article that might have something to do with that question, so we can check that out. Jane would like to ask a question. Evergreen trees would have more evapotranspiration than hardwoods in the winter. Changing the species you manage for might be something you could do, but it might have very little effect. What are your thoughts on that?
Yeah, and I would agree with the last part of that statement, is that you probably could do some species modifications to have small effects, but it's probably going to be a fairly minor effect in the overall scheme of things. So I don't know that it's going to have a big effect, but yeah, you might get a little bit of extra ET out of how you manage or what species you manage for.
Mm-hmm. Yeah, Mike is listing some other ways you can address restoring hydrology and hydrologic connections. So road treatments, re-engaging streams with abandoned floodplains, right-sizing road stream crossings. And this might be a good place too to mention a new award from the USDA climate hubs that will in the coming year address the national USDA Wilderness and Wild Scenic Rivers program. And the goal there is to create a guidebook for fully integrating climate change into comprehensive river management plans. So that is something that will be under development and might be able to help address some of those watershed focused strategies as well. We also, as part of the forest adaptation workbook, have the forested watersheds adaptation menu, which is just a list of potential adaptation actions you can take. The idea there is that you would select the ones that are most relevant to the place that you're working in and the impacts that you're facing, and then work to implement those strategies in a very specific way. So we can provide a link. Oh, Maddie's on top of it. That's in the chat box. We have a few more minutes for questions. So what else do you have for us?